Hi, good morning, everyone. So we are from the team 8. We are going to discuss today about our project Landslide Detection with multispectral satellite imagery using deep learning models. So this project is linked to the CNST project as it deals with the landslides which are most important towards this era. So in this project, we are going to discuss what are landslides, how are they going to affect in the future cases of the soil and all. So basically, what I'm going to tell about this firstly is the landslides. Landslides are large movements of rock, soil, or debris down a slope, often caused by natural or man-made factors. You can think of it like a huge chunk of earth suddenly sliding downhill. These movements can be extremely dangerous. They destroy houses, roads, and even some entire cities can be destroyed by the landslides. We can even observe in the Japan and other cities which are happening. These are all due to landslides. The earthquakes and all are some are similar to landslides. And these are mainly caused by heavy rains, earthquakes, steep slopes, and even the volcanic eruptions, which are gonna affected by the lava flows. On this slide, we're gonna discuss about the problem statement. Despite the advances in technology, traditional landslide detection methods still rely heavily on manual surveys and field inspections. These methods are slowly and expensively becoming dangerous. The core problem we are trying to solve is how can we detect landslides quickly and accurately using modern data mining and AI techniques? How can we use these techniques to detect and predict the problems? The faster we detect the landslides or landslide prone areas, the more lives we save and more resources we can store. And to the next slide. Oh yeah. So the objective and scope. So our main objective of this project is to build a system that can detect landslide affected areas automatically from satellite imagery. We aim to use deep learning to perform pixel level segmentation, which means it will not only predict whether the area is a landslide or not, but exactly it's gonna detect where on the image the landslide area is located. And the scope of our project is we are focusing on a multi-regional dataset collected from diverse geographic locations. As you can see, the locations are from Karnataka, Nepal, and from Japan. So we are basically focusing on multi-regional dataset collected from different areas to ensure our model works fine and good. These are mainly caused by rain, earthquakes, slope failures, and our main work is to use the satellite imagery data and the elevation data and prepare it for the deep learning model which we are going to use and predict the accurate landslide segmentation. In this data set, we are considering these three locations. As I told earlier, the first one is from the Japan, second is from the Karnataka, India, third one is from the Rasua area from Nepal. So we choose these areas because these are all geographically different and the areas that are affected by the landslides. And also we have used two satellites that are Sentinel-2 and ALOS PALSAR. These two satellites, each the ALOS PALSAR has emitted two bands and the Sentinel has emitted 12 bands which are different. So there are totally 14 bands that are emitted from the satellites to observe and get an accurate precision areas of landslide predictions. From now, my friend Shashank gonna continue. Yeah,
Yeah,
as
as
Adi
Adi
discussed,
discussed,
like we
we
have
have
collected
collected
the
the
data
data
set
set
which
which
has
has
these
these
areas
areas
from the
from the
landslide
landslide
for
for
sense
sense
competition
competition
conducted
conducted
by
by
IARAI.
IARA thing. Then discussing about the data set, we have many bands in the data set for a single image. We have like as you see from the band 1 to band 14, and then we also have the ground truth attached to it. Coming to the details of the band 1 says it is like ultra blue emission. The band 2 to band 4 describes the RGB, and then 5 to 8 it says visible and near infrared, then short infrared, and the 14 bands are the slope and DEM. So so now from these bands we gonna interpret like combining some bands and then training it to the model. Like we have taken here the vegetation index. It's like the likely when we take the vegetation index, the likelihood of the landslide occurring in the abundant vegetation, like the roots uphold the soil very tightly in the large vegetation areas. So it helps the landslide occurrence as low, as we have like when the vegetation is very high, the occurrences of landslide will be very low. Here we are taking, as we see, the formula is like the calculation of NDVI index is band 8 minus band 4 by band 8 plus band 4. And then the moisture index, like we consider this because when we have the lots amount of moisture present in the soil, like it helps the occurrence of landslide. So we calculate the moisture index and feed it to the model. And then also we take the slope and DEM, which is when there is steeper slopes, it will be the high risk to prone a landslide. And we also take the elevation data. These DEMs like helps us to capture the shape of hills, valleys, slopes, etc. And then we pre-process the data, like if any missing pixel values are present, we'll make it as a near zero. And then for the slope and elevation, we have normalized it to -1 to 1 using the normalization. And then we have split the data into training, testing, and validation. As you see in the image, we have like 70% training, 15% validation, 15% for testing. And then we have two methodologies incorporated here. Like we have used the FCN model and the unit model, like to compare the different results. Like the FCN model, we have the encoding decoding phase here listed below. Like we have generally used it for the comparison of model, how the model performs like when compared to other architecture. And then our main proposed architecture is the unit architecture. Like as we see here, this is the unit architecture we are using here in the proposed model. To follow, like we have the 4-layered unit model consisting of encoder and decoder layers. Like each image has a dimension of 128 into 128 pixels. Like we have used the sample input as the final F1 score, which we got like the highest score. We have used these bands to describe in the image. And then like coming to the model architecture, we have four encoding and decoding layers. Each layer has like 128 into 128 pixels. And like we have given the four channels as in input, which is NDVI, NDMI, DEM, and slope. And this encoding phase is responsible for the downsampling and the input features to extract the high level representations from the beginning layer. This repeats for the several blocks, and each block doubles the number of filters. So we have the image size to the half, and then it reaches the bottom neck layer and then decodes. Now the decoding part will be explained by Nagesh.
Yeah, coming to decoding phase, upsampling and output. After encoding, the model starts decoding by upsampling the image to get back to the original size. And upsampling helps to recover the lost detailing during encoding. And we use skip connections. They can connect encoding and decoding layers to pass important features directly, making the model better. And the final output becomes 128 in 128 pixels again. The formula shows tells how output size is calculated after upsampling. Finally, a sigmoid activation function is used in this last layer. This gives a value between 0 and 1, helping to classify each pixel as the landslide or non-landslide. And coming to next slide, in this slide, I'm going to discuss about the class imbalance and YF1 square. In satellite images, landslides are very small compared to the background. If we simply use accuracy, the model can cheat and predict everything as background and still look accurate. That's why FN square is better. FN square, FN score checks precision, how many predicted landslides are really correct. Recall is going to predict how many actual landslides did the model detect. FN square balances both precision and recall, helping us to know if the model is really good at finding landslides. And coming to the next slide, we're going to discuss on precision recall. Precision recall individually are not enough. If the model has high precision but low recall, it predicts few landslides correctly but misses many real ones. And high recall but low precision, it detects most landslides but gives many false alarms. In landslide detection, both missing landslide like a false negative and giving too many false alarms, false positive or bad. And F1 square balances both, making the model reliable and in real world use very safety important, where it is important. And next slide is going to explain by Shanmugh.
So moving forward into the presentation, so here are the results of the implementation of the explained model. So we have compared various models like our proposed model UNet and FCN with the various combinations of the input bands. So the various combinations are shown in the left of the table. So right from the single most variables like RGB, vegetation index, and the moisture index, we go on incrementing the various combinations, and we see an steady and an uniform performance of the model in the with the following combination of moisture index, vegetable index, and the slope, and DEMI. So yeah, in the next slide. So these are the learning curves of the proposed unit model. So we can observe an steep learning, proper learning rate until the 60th to 80th 60 to 80 of ox. Later then we can see an divergence of the curve. We must have used an early stopping, but so in order to uh, see the working of the unit model, we let the model to by stop by itself, and these are the results. So moving forward into the testing, test predictions of the unit model. So same as from the validation test, we can see the first bar plot represents the proposed combinations of the futures. And yeah, moving forward, so these are the F1 scores, which are mainly compare used in this because of the imbalance of the data. So the proposed combinations is in the last, which has the highest F1 score of 0.772. And so here is a sample prediction of the combination. So the first one is the NDMI, and the second one is the vegetation index, and the slope, and the DEM. So the prediction this is the ground truth, and the prediction is in the last column. We can see a few missing in the predictions, but on visual evaluation, but in future implementation, we can uh, find out the reason for the misclassification and work on it. So coming to the conclusion and the future works guidance. So we have worked on an fully connected unit model and an FCN model and we also figure out few of the combinations of the futures which might lead give you an higher prediction rate. And we have achieved an F1 score of 0.72. And the future works of this kind, as I said earlier, when we talk about the future works, so we can find out the reason for the misclassification or evaluation of the uh, misclassification, and work on implementing the model performance, and reducing the complexity of the model. And these are the references used for the for the implementation and code references. And thank you for giving us this opportunity. Have a nice day.